So, hello, my name is Jelizaveta and I'm from Cybernetica. And I'm going to talk about this is talk based on our paper that we wrote for the SciCon this year, the conference hosted by NATO CCDCOE. And the paper was about the obstacles of migration of Estonian digital services to post-quantum cryptography. And here I linked the paper. You can scan it and find the paper itself. I will tell you now that there is no math involved. It is just high-level introduction of post-quantum cryptography and some obstacles without any formulas or something complicated. So, yeah, the motivation behind our paper. As far as you know, Estonia is known worldwide for its usage of different e-services, various digital identity solutions, like the iVoting and those digital signatures that we do with the ID cards. And all of this infrastructure heavily relies on cryptography. How the public key cryptography works is that we have some hard mathematical problem and we build our crypto systems on top of those mathematical problems. And then most of the current public key cryptography is built on two problems, factorization problem and then discrete logarithm problem, or the elliptic curve discrete logarithm problem. And it is known that there is a quantum algorithm that can break those problems, meaning that when we will be having sufficiently powerful quantum computer, the adversaries will be able to break our existing public key cryptography algorithms. Therefore, there is a really big need to switch all the systems from those modern public key cryptography algorithms like RSA, ECDSA, ELGAMAL, Schnorr, and many others to the quantum safe alternatives. Not this way. Yeah. So here is the table of some of the most popular public key cryptographic algorithms and where those algorithms are used in the various digital identity solutions in Estonia. And as you see, the first 4 rows correspond to the public key encryption, digital signatures, and the key establishment, and all of those will be broken once large enough quantum computer will be available. And those algorithms are the ones that are behind the smart ID, authentication and signing, ID card, X-Road, iVoting, mobile ID, and public infrastructure in general. And then I added this last row to emphasize that there is an impact to the symmetric cryptography as well, meaning the block ciphers and the hash functions. But those primitives are not completely broken as the public key cryptography. We just need to increase the key size for the block ciphers and then the output length for the hash functions, and we will be fine. Before we go deeper into the presentation, let us refresh what the post-quantum cryptography is. I want to ask how many of you have heard about post-quantum cryptography before? Raise your hands. Okay. So it is really important to emphasize that there are 2 different words, post-quantum cryptography and quantum cryptography, and those are totally different things. So the post-quantum cryptography, the thing that I'm focusing in my presentation, are the algorithms that work on our regular computers and even mobile devices, but are resistant to the attacks of quantum adversaries. You do not need any special hardware to run post-quantum cryptography. It is just resistant to attacks of quantum computer. And then there is another world that is quantum cryptography, and for quantum cryptography we need dedicated devices. Like one of the most known examples of quantum cryptography is quantum key distribution. For that, you need those special transmitters that transmit photons. So you will do this quantum physics magic in it. And I'm not focusing on the quantum stuff here. And I decided to add one more slide to kind of tell you what are the biggest differences between those two, because those are really mixed together when you read the literature and talks and etc. So the post-quantum cryptography provides us really wide range of applications. We can do encryption, we can do digital signatures, key establishment, and also some fancy stuff like zero-knowledge proofs that are used in blockchain now, commitments, and the homomorphic encryption, and all that stuff. And post-quantum cryptography, as I said before, works on classical computers, and the security of those primitives relies on some hard mathematical problems, and examples of some mathematical problems for the post-quantum cryptography are learning with errors and short integer solution, the problems that are there for the lattice-based cryptography. And then about the quantum key distribution, as the name suggests, it is only the key distribution. So you can only distribute the secret key between the two parties, and then you can, of course, use the secret key to encrypt the communication, but it only allows you to encrypt. You cannot create signatures, you cannot do authentication, you just establish the keys, and that's all. It requires some special devices. It is not working for long distances. You need to put some trusted nodes in the path if you want your QKD to work for longer distances, and all this is very costly. But why it is so popular now is because its security relies on the fundamental principles of quantum mechanics, saying that it's kind of unbreakable. That's why it seems to be fancy, but it's actually not that fancy. And then when talking about the post-quantum cryptography, a common question is, okay, but when do we expect this sufficiently powerful quantum computer? And this is a really good question, and there is no really great answer to that, any strict deadline where this quantum computer will be available. And the source that I like using is this quantum threat timeline report that is issued, I guess, every year. What they do there, they ask different quantum field experts to estimate, worldwide experts estimate what is the probability of having such a large quantum computer in next 5, 10, 15, 20, and 30 years. And then they kind of put their answers in this graph, and you can see that kind of really important threshold is next 15 years, because the majority of the experts thinks that there is a 50% or even likely chance to have such large quantum computer that will be able to break RSA with 2048-bit keys. This is kind of the key length that is most commonly used right now for the RSA. So 15 years is the deadline that we should be kind of preparing for. What is there in our work? We gave an overview of current status of post-quantum cryptography, what different organizations recommend to use, which algorithms, what are the commonly known obstacles. We also, the main focus was to identify what are the challenges that are particular to Estonia and Estonian services, and we focused on those, I guess, most widely known and used services like Smart ID, ID card, X-Road, public infrastructure, and iVoting, and I will be telling about them more in details later. So what is the current state of post-quantum cryptography? More details can be found in the paper, but the minimum that you need to know. There is a NIST, National Institute of Standards and Technology, in the US, and they are responsible for issuing the standards for cryptographic algorithms. And in 2016, they initiated this project of trying to find the algorithms that are secure against quantum computers. And last year, I guess it was last year, they selected the finalist schemes for the key establishment and digital signatures. And hopefully, well, right now there are standard drafts for almost all of those algorithms. And hopefully by the end of this year, we will be having the standards themselves. And the algorithms that are there for the digital signatures are called Crystals, Delphium, Falcon, and Sphinx Plus. First two, if you're interested, are based on lattice-based cryptography, and Sphinx is based on hashes. And then for the key encapsulation, we currently have just one algorithm, that is Crystal Skyber, based on lattices. And for both digital signatures and key encapsulation, there are currently additional rounds running in NIST, trying to find more algorithms to add variability to this kind of toolbox. Because right now we kind of can have RSA that is based on factorization. We can have ECDSA that is based on the elliptic curve discrete logarithm. So you kind of have a bit different mathematical problems underlying the security of the schemes. And for the post-quantum world, we also would want to have something not just all based on one math, a bit different kinds of math. And the important thing that you can find in almost all the publications talking about post-quantum cryptography is a hybrid mode. What it means that you are using post-quantum cryptography together with the pre-quantum cryptography, like pair crystals dilithium with RSA. And why it is advised to do so? Well, because although there is kind of really extensive research in post-quantum algorithms, we are not yet entirely sure in their security, mostly regarding the side channel attacks, because, well, you cannot really design algorithm really protected against side channel attacks. It's your implementation that should be protected against those. And then the other thing is that we need to support legacy devices that are still running this RSA, ECDSA, etc. So for the period of transmission from pre-quantum cryptography to post-quantum cryptography, it is kind of considered to be a good practice to use post-quantum cryptography together with the pre-quantum cryptography to smooth the transition period. And now let's talk about the Estonian digital services and what are the problems with them. So the most fancy thing and the most interesting for me, because this is like mostly my research, is Smart ID. So the Smart ID is authentication and signing solution, and it relies on threshold cryptography. What is it? When you are creating your regular digital signatures with the ID card, for example, with the smart card, inside the smart card you have the secret key and you create the digital signature using your secret key. But if you want to use your mobile device, it implies that you would need to store your secret key on the mobile device, which is not that safe because, well, it is easy to attack mobile devices versus the smart cards. You cannot really extract the key from the smart cards, but with the mobile devices it is easier, of course, if you're not using some trusted execution environment. And instead of this trusted execution environment, we decided to use threshold cryptography, meaning that the secret key that should be stored inside the mobile device is split into two parts. One part is stored inside your mobile device, the other part is stored on a supporting server. And when you need to authenticate to some service or you want to create digital signature, you apply on your mobile device the first part of the secret key. You send this part of the signature to the supporting server. Server applies their share of the signature, and then you have the final signature that is verifiable by a single public key. When we want to select an algorithm that is more appropriate for the Smart ID, among the ones that will be standardized by NIST, the most suitable one seems to be crystals dilithium, just because on its mathematical structure, it allows to do some fancy computations within it. So we decided in our research to kind of stick with the crystals dilithium. But there is a problem with the crystals dilithium, and the problem is called rejection sampling. What does it mean? You run your signature algorithm until almost the very last step, when you have your almost signature ready, and then the signature needs to pass a few checks to verify that the signature does not leak a secret key. It's like here. You are checking the signature, and if at least one of the checks fails, you need to restart the signing algorithm again. until the valid signature is found, and then you can output the signature. And it is not really a problem for the applications that are using like the signature locally. You just restart signing process a couple of times, 4 or 5 times if I remember, for the parameters that will be standardized. And this is not a big issue. It's still quite efficient in its running time. But when you want to distribute the signing process, having the client to create half of the signature and then the server create half of the signature, you will need to do those checks on the signatures in both sides, and it will imply that the number of restarts that you need to satisfy the checks on the client side and on the server side is much bigger. So you need a bigger number of restarts. And of course, each time you restart, if you redistribute the protocol, it will be the protocol, not the algorithm. You will need to do some interaction, send messages back and forth between the server and the client. And you need to repeat all these messages for each time you restart. So this is really a big problem that we need to sort. And another issue is that there are some algorithms that are kind of more suitable to be distributed, but those are not considered to be standards in any future time. But if we want to provide the same service as it is now, so like if you create your digital signatures with Smart ID, this is considered to be qualified signature creation device. That's why the signature is legally binding. And to achieve this, your signature needs to be compliant with the standards. So you cannot just take whatever algorithm is there that is secure and that works with math better than the lithium and be happy. You need to somehow stick with the standards and try to fight the standards to make the signature work. Next, again related to digital signatures, we have the ID card. With the ID card, right now you can sign your documents, and also it has the encryption functionality. So I'm not sure how many of you have used the encryption functionality with the ID cards. Have you encrypted the documents? Surprisingly many. So yeah, you know that there is this encryption functionality, meaning that the ID card needs to store the keys for the signatures and for the encryption as well. But currently we have this beautiful algorithm RSA that kind of allows you to do both digital signatures and encryption decryption. And it is great that one algorithm, DanMath, supports all of this. But in the post-quantum world, we do not have any one algorithm that gives you the same functionality. Even though those crystals, the lithium and crystals Kyber, belong to kind of the same family, the algorithms are quite different, and you need to do different operations when they run, and you need to store those pairs of the keys inside the ID card. Other thing is that, as you can imagine, the smart cards are quite constrained devices, but the post-quantum cryptography, mostly the algorithms, well, I guess not mostly, just all the algorithms that are there in post-quantum cryptography are much more complicated in terms of math than the currently used algorithms. That's why it is kind of harder to run those on the constrained devices. And as far as I know, somebody tried to run the lithium, but I don't know if they succeeded in that or not. So this problem should be somehow tackled. Either the chips should be more powerful, or I don't know what, but we somehow need to solve the problem of smart cards currently not supporting post-quantum cryptography at all. Another important thing regarding the smart cards is side channel protection. So the side channel attacks are those when you kind of measure the time when the algorithm runs. Like imagine the signature is being created and you measure the time that is needed to create one signature or decrypt the document, or you measure the power consumption or whatever. And those are called the side channel attacks. And in post-quantum cryptography, those side channel attacks are a really big problem. And there is, right now, as we know what will be the standards, there is quite extensive research on how to protect against those side channel attacks, but we can still be sure that we are 100% protected. And with the smart cards, it is a really big problem to be thought of. iVoting. Now moving to bigger systems. Before we talked like only about the signing and encryption, but if you think of iVoting, there are much more things involved in the protocol. You need some fancy encryption that allows you to do the computations on the ciphertexts called homomorphic encryption. You need obviously digital signatures to sign your ballots when you send them. You need some zero-knowledge proofs to prove that the computations on the votes were done correctly, the decryption was done correctly, etc. Then you need the mixnets to randomize the ballots before they are being tallied and decrypted. And that's why we need to find kind of alternatives to all, well, those are not all building blocks, just like example building blocks. And you need to find post-quantum alternatives to each of the block. And the problem is that there are some solutions currently available, but they are not really showing great performance. And the problem is that you cannot find like really one-to-one alternative if you take like current system that is pre-quantum and try to like map digital signature to post-quantum digital signature, homomorphic encryption to post-quantum homomorphic encryption. Not all the primitives have this like one-to-one match, and you maybe need to restructure the whole iVoting process and rebuild the whole protocol from the ground up. Then I kind of unified the public key infrastructure and X-Road because they have pretty much the same challenges in them. So X-Road is this layer that allows to exchange data between different institutions or companies in a secure encrypted form. And here, since here we do not have like any fancy cryptography, we basically need just digital signatures and key establishment. So here we can start talking about those hybrid things that I told you before. Of course, the whole hybrid talk may be related to all the previous solutions that I showed you, but there are like many more important problems to work with before we kind of move to the hybrid thing. So we need to somehow, we have our certificates that have our say ECDCA keys, and we need to establish this hybrid certificate infrastructure. So we will have both keys, the pre-quantum and post-quantum inside the certificates. There are different solutions out there. Some of them adding those keys to this alternative public key extension. Some of them suggesting to do like parallel public key infrastructure. One is like pure post-quantum, the other is pure pre-quantum. Each of them have their advantages and disadvantages, and the one that should be chosen heavily depends on your requirements within your system, how many of the legacy devices there are in your network, how many you want to support, etc. And the other open question for the public key infrastructure is how to combine the signatures themselves. Because with the key establishment, it is like pretty easy. You can run regular Diffie-Hellman key exchange, then you run this post-quantum, this Crystal Kyber. You get those shared secrets from both of them, and you input them to the key derivation function, and you get yourself the key that is derived from both pre-quantum and post-quantum. Everything great, seems to be like working fancy. But with the signatures, it is a bit more complicated because well, the simplest way you can concatenate signature, take the RSA and plug in the Crystal Kyber, Crystal Dilithium. But maybe you also want to somehow like connect them. Maybe you want your post-quantum signature to sign pre-quantum signature to like create this connection between them. So this is like big open question as well. And the conclusions of our work were that actually there are only a few obstacles that are the same for all the systems that we looked at, and mainly because like the systems themselves, they are based on different architecture, they have different security requirements and functional requirements. That's why the problems are also different for them. The thing that is kind of similar to all the solutions is the increased size of the key signatures and ciphertext. Because we changed the math, it led to increased size of the public keys and the signatures and the ciphertext. There is nothing we can do. We need the strength to select the algorithms that are like more, have smaller keys and signatures, but I guess so far we need to live with the increased sizes. And the other important thing is that there is no one scheme that will be suitable for all the use cases. Because for now you can take ECDSA signature and basically use it everywhere. It is fast, it has like small signatures and keys, and it is great. But with the post-quantum cryptography, it will no longer be the case, because each of the scheme has its own advantages and disadvantages. Some work faster but have larger keys, some are like less efficient but have smaller keys, etc. So you need to identify what is important for your application and then choose the scheme that will be suitable for your solution. Oops. I'm not sure what should I do. Well, I can talk because you can read after that. So the important topic is education, because the post-quantum cryptography seems to be very like terrifying, complicated, and people are scared of talking about it and looking into it. And I told you that the algorithms are really complicated, and being a cryptography teacher, I see that it is much harder to explain to students how post-quantum cryptography works. But if we are not focusing on the math part, the hard part, the education also needs to be done in the whole migration thing, because people are not believing that we need to start worrying, but we actually need, because the process of transitioning from the one algorithm to another, it is a long process, especially if you need to, for example, if we take those ID cards that are like obligatory for each citizen of Estonia, you need to somehow find a suitable ID card that will be doing post-quantum cryptography. You need to certify this card. Then you need to somehow redistribute those cards within Estonia. So this is really, really long process. That's why we need to start worrying. We need to start having those migration strategies ready to be there when the quantum computer will be available. And I want to kind of promote our website. Those are like clickable links if you will have access to the slides later. So we have the blog post where mostly I'm talking about the post-quantum cryptography and like simple words of, again, the obstacles and some of the post-quantum solutions that we are in Cybernetica working on. And also we have the YouTube channel. There was recently a conference organized by our company that was called Future of Cryptography, where we were focusing on the post-quantum cryptography, and the recordings from the conference are there in YouTube, so you can watch in more details. There are some talks about like more math involved, some are like more on architecture level, very interesting things. And something funny, since we're working on the post-quantum cryptography and we see that there is this education big problem, we also developed a board game that we presented last week in Oxford conference. And this board game is meant to show how the migration process works, what are the challenges in the migration process, so the people start understanding that it is not so easy to just take one algorithm and plug it to the place and everything will be fine. And more information about the game will be also available on the website. I wanted to bring it today, but I forgot to take it with me. But if you will follow our website, you'll find information about that soon. And that's it from me.